Nenomatica, where mathematics meets YouTube excellence. Welcome to this educational video on basic inequalities. Today, we're going to explore an important inequality theorem and work through its proof step by step. Let's start with the theorem we'll be proving today. If n is an element of n, which represents the set of natural numbers, then k times n minus k plus 1 is greater than or equal to n, where k is between 1 and n inclusive. Let's analyze what this theorem is telling us. It states that for any natural number n and any value k, where k is between 1 and n, the expression k times n minus k plus 1 will always be greater than or equal to n. Now, let's begin our proof. We start with the constraint that k is between 1 and n. From this constraint, we can derive two important inequalities. First, k minus 1 is greater than or equal to 0. Second, n minus k is greater than or equal to 0. These are straightforward to see since k is at least 1, so k minus 1 is at least 0. And since k is at most n minus k is also at least 0. The next step in our proof is to multiply the two inequalities we derived. We multiply n minus k and k minus 1, which gives us n minus k times k minus 1 is greater than or equal to 0. When we expand this product, we get n times k minus n minus k squared plus k, which is greater than or equal to 0. Let's continue by rearranging the terms in our inequality. First, we move all terms except n to the right side, getting nk minus k squared plus k is greater than or equal to n. Now, let's factor out k from the left side. We get k times n minus k plus 1 is greater than or equal to n. And that's exactly what we wanted to prove. We've shown that k times n minus k plus 1 is greater than or equal to n when k is between 1 and n. Now, let's look at another important inequality theorem. This theorem states, for all a, b, and c in the set of real numbers are 3 times the sum of products, ab plus ac plus bc is less than or equal to the square of the sum of plus b plus c, which in turn is less than or equal to 3 times the sum of squares a squared plus b squared plus c squared. This is another powerful inequality that relates the sum of products, the square of a sum, and the sum of squares. Let's start the proof of this second theorem. First, let's expand the square of the sum. The square of a plus b plus c equals a squared plus b squared plus c squared plus 2 times ab plus ac plus bc. We recall the AMGM inequality, which tells us that a squared plus b squared plus c squared is greater than or equal to ab plus ac plus bc. This is a fundamental inequality in mathematics. Using this inequality, let's multiply both sides by 2. We get 2 times a squared plus b squared plus c squared is greater than or equal to 2 times ab plus ac plus bc. Now, substitute this into our expansion of the square. We get a squared plus b squared plus c squared plus 2 times ab plus ac plus bc is less than or equal to a squared plus b squared plus c squared plus 2 times a squared plus b squared plus c squared. Simplifying the right side, we get a squared plus b squared plus c squared plus 2 times ab plus ac plus bc is less than or equal to 3 times a squared plus b squared plus c squared. Rearranging the left side, we get the square of a plus b plus c is less than or equal to 3 times a squared plus b squared plus c squared. Now, let's prove the left inequality. From our expansion of the square, we know the square of a plus b plus c equals a squared plus b squared plus c squared plus 2 times ab plus ac plus bc. We can rearrange this to get 2 times ab plus ac plus bc equals the square of a plus b plus c minus the sum of squared plus b squared plus c squared. Multiplying both sides by 3 over 2, we get 3 times ab plus ac plus bc equals 3 over 2 times the square of a plus b plus c minus 3 over 2 times the sum of squared plus b squared plus c squared. We already proved that the square of a plus b plus c is less than or equal to 3 times a squared plus b squared plus c squared. Substituting this into our equation, we get 3 times ab plus ac plus bc is less than or equal to the square of a plus b plus c. Combining both parts, we have proven that 3 times ab plus ac plus bc is less than or equal to the square of a plus b plus c, which is less than or equal to 3 times a squared plus b squared plus c squared. Let's summarize what we've learned today. We proved 2 important inequalities. First, for natural numbers, k times n minus k plus 1 is greater than or equal to n when k is between 1 and n. Second, for any real numbers a, b, and c, 3 times the sum of their products is less than or equal to the square of their sum, which is less than or equal to 3 times the sum of their squares. These inequalities have numerous applications in mathematics, including optimization problems, proving other inequalities, and solving various real-world problems that involve minimizing or maximizing quantities. Welcome to our math video. Today we're going to explore a fascinating theorem about basic inequalities and prove it step by step. Let's start by stating the theorem. For any positive real numbers, a, b, and c, if a squared equals b squared plus c squared, then we can conclude the following. If n is greater than 2, then a raised to the power n is greater than b raised to the power n plus c raised to the power n. And if n is between 0 and 2, then a raised to the power n is less than b raised to the power n plus c raised to the power n. Now, let's prove this theorem. We start with our given conditions. We know that a, b, and c are positive real numbers, and a squared equals b squared plus c squared. For our first step in the proof, we'll rewrite b to the n plus c to the n in a clever way. We can express b to the n plus c to the n as b squared times b to the n minus 2 plus c squared times c to the n minus 2. For the next step, we'll use a key property. Since n is greater than 2, and we know is greater than b and is greater than c, we can say that a to the n minus 2 is greater than b to the n minus 2 and also greater than c to the n minus 2. This means we can replace b to the n minus 2 and c to the n minus 2 with a to the n minus 2, and the inequality will still hold. Now, we can factor out a to the n minus 2 from the right side of the inequality. This gives us b to the n plus c to the n is less than a to the n minus 2 times the sum of b squared plus c squared. Remember that one of our initial conditions was a squared equals b squared plus c squared. So we can substitute a squared for b squared plus c squared in our inequality. Finally, we can combine the exponents on the right side of the inequality. A to the n minus 2 times a squared equals a to the power of n minus 2 plus 2, which simplifies to a to the n. Therefore, we've proven that b to the n plus c to the n is less than a to the n when n is greater than 2. Welcome to our mathematics video. Today, we're going to explore basic inequalities theorem 7 and provide a step-by-step proof. Let's first understand the theorem statement. If n is a natural number and a and b are positive real numbers, then the following inequalities hold. Let's proceed with the proof of this theorem. Let's begin with the first part of the proof. If it is greater than or equal to b and greater than 0, then a to the power of n minus 1 is greater than or equal to b to the power of n minus 1. This implies that the difference between a to the power of n minus 1 and b to the power of n minus 1 is greater than or equal to 0. Since it is greater than or equal to b, we can say a minus b is greater than or equal to 0. Next, we can say that the product of a minus b and a to the power of n minus 1 minus b to the power of n minus 1 is greater than or equal to 0. When we expand this expression, we get a to the power of n minus a times b to the power of n minus 1 minus a to the power of n minus 1 times b plus b to the power of n, which is greater than or equal to 0. Rearranging this inequality, we get a to the power of n plus b to the power of n is greater than or equal to a times b to the power of n minus 1 plus a to the power of n minus 1 times b. Now, for the second part of the proof, we'll show that a to the power of n plus b to the power of n is greater than or equal to a times b times the sum of a to the power of n minus 2 and b to the power of n minus 2. Let's consider some examples to see how this theorem applies in specific cases. Note that the proof for the case when it is less than b follows a similar approach to what we've shown. Welcome to our mathematical proof video. Today we're going to explore and prove the Bernoulli inequality theorem, which is a fundamental inequality in mathematics with numerous applications. Let's start by stating the first part of the Bernoulli inequality. This inequality states that for any real number greater than -1 and any integer n greater than or equal to 0, or when n is greater than or equal to 1, we have 1 plus a raised to the power of n is greater than or equal to 1 plus n times a. Now, let's prove this inequality using mathematical induction on n. We'll start with the base case. For n equals 2, we have 1 plus a raised to the power of 2 equals 1 plus 2 a plus a squared. This is clearly greater than 1 plus 2a, since a squared is positive when it is greater than -1. So the inequality holds for n equals 2. Now, let's state our induction hypothesis. We assume that the inequality holds for n equals k, meaning that 1 plus a raised to the power of k is greater than 1 plus k times a. For the induction step, we need to prove that the inequality holds for n equals k plus 1. That is, 1 plus a raised to the power of k plus 1 is greater than 1 plus k plus 1 times a. To prove this, let's start by expanding the left side. 1 plus a raised to the power of k plus 1 equals 1 plus a raised to the power of k times 1 plus a. Now, using our induction hypothesis, we know that 1 plus a raised to the power of k is greater than 1 plus k times. Multiplying both sides by 1 plus a, which is positive since it is greater than -1, we get that 1 plus a raised to the power of k plus 1 is greater than 1 plus k times a times 1 plus a. Let's expand the right side of the inequality. 1 plus k times a times 1 plus a equals 1 plus a plus k times a squared, which simplifies to 1 plus a plus k times a squared. We can rearrange this to 1 plus k plus 1 times a plus k times a squared. Since k times a squared is positive for a greater than -1 and k positive, we can say that 1 plus k plus 1 times a plus k times a squared is greater than 1 plus k plus 1 times, which gives us our desired result. 1 plus a raised to the power of k plus 1 is greater than 1 plus k plus 1 times a. It's important to note that this inequality holds under the condition that 1 plus o is greater than 0, which means o is greater than -1. This inequality is known as Bernoulli's inequality and has many applications in calculus and other areas of mathematics. There's also a second part to the Bernoulli inequality. When 0 is less than or equal to n is less than or equal to 1, the inequality is reversed. 1 plus a raised to the power of n is less than or equal to 1 plus n times a. The proof of the second inequality follows similar steps and can be proved in the same manner as we did for the first inequality. Welcome to our video on basic inequalities. Today we'll discuss an important inequality theorem and walk through its proof step by step. Let's start with the statement of Theorem 9. If x plus y equals k, where k is greater than 0, and n is an element of the natural numbers, then x to the power of n plus y to the power of n is greater than or equal to k to the power of n divided by 2 to the power of n minus 1. Now let's prove this theorem. We'll start with a reminder of a key inequality that will help us. The arithmetic mean power mean inequality states that the quantity x plus y divided by 2 raised to the power of n is less than or equal to the quantity x to the power n plus y to the power n, all divided by 2. Now, let's apply our condition. We know that x plus y equals k. So, the left side of our inequality becomes k divided by 2, all raised to the power of n. Therefore, we have k over 2 raised to the n is less than or equal to x to the n plus y to the n, all divided by 2. Now, let's manipulate this inequality to match our target form. Multiplying both sides by 2, we get k over 2 raised to the n times 2 is less than or equal to x to the n plus y to the n. This simplifies to x to the n plus y to the n is greater than or equal to k to the n divided by 2 to the power of n minus 1. And that's exactly what we wanted to prove. Let's also note an important condition for equality in this inequality. The necessary and sufficient condition for equality is when x equals y equals k over 2. This means that equality holds when both variables are equal to half of their sum. Finally, it's worth mentioning that when n equals 1, the inequality becomes a simple equality. This is because when n equals 1, the right side becomes k divided by 2 to the power of 0, which is just k. And we know that x plus y equals k from our initial condition. In conclusion, we've proven Theorem 9, which states that if x plus y equals k, where k is greater than 0, and n is a natural number, then x to the power of n plus y to the power of n is greater than or equal to k to the power of n divided by 2 to the power of n minus 1. This inequality is a powerful tool in mathematical analysis and optimization problems. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.